Okay, so let's practice with this example. Uh, this example is about the uh, finding the pH calculation to find the pH of salt or the polyprotic acid. Okay, now let's look to this example here. Okay, so here we have this example. Estimate the pH of 0.1 molar NH4 NiO3. The Ka is 5.6 times 10 to negative 10. Write the equation for each ion water. Now, what do we have? We have ammonium nitrate, NH4, NH3. Will dissociate to positive, NH4 positive, and NO3 negative. Now, each of them will react to the other with water. NH4 positive plus H2O will give you H3O positive and NH3. The NO3 will react with the water to give OH negative and HNO3. Now, going from weak, here, weak base. Guys, look at here. Strong, just to give you how to decide weak or strong. Let's finish it. From weak to strong, that's not happen. Cannot happen. Going from weak, going from kind of weak or strong, a little bit strong, to weak, it's gonna happen. So here, I will give you some idea about how to decide which one is strong, which one is weak. We have strong acid, HCl, HNO3, H2SO4, HBr, HR, and HClO3, for example. These strong acid, they give weak conjugate base. So here Cl negative, NO3 negative, SO4 2 negative, Br negative, I negative, ClO3 negative. So these are guys here at ClO4 also. ClO4, ClO4 negative. So these consider weak bases, weak conjugate bases for the strong acid. So that's why I decide NO3, it is a weak. So look at here, NO3. It is a list of the weak. So NO3, it will give you, it will go to give you the strong. So that's not gonna happen. Now, for bases, also for NaOH, for example, strong bases, NaOH, LiOH, KOH, it's strong. And these, it will give you weak conjugate acid. Weak conjugate acid, yes, sodium, lithium. passive. So this is weak, this is strong. Now, the weak acid, it will give you kind of stronger conjugate base. That's why I decided NH4 positive is a little bit stronger. Why? Because NH3 give me NH4 positive. Sorry, this is acid. We are talking about acid. No, not NH. Like, for example, H2CO3. Give me CO3 to negative. So it is a little bit stronger. The same idea. Weak base. Give me a little bit stronger conjugate acid, like ammonia, NH3, NH4 positive. That's why I decided here NH4 positive a little bit stronger, NH3 is weak, so it can happen. So that's how you will decide if that could happen or not. For reacting with the water. Okay, let's go back here. So we will have, we said this one, no, will not happen. So we have NH4 positive, reacted with H2O, give us H3O positive plus NH3. So we can make an ice table for it. So here, we will have the ice table. Water, nothing here. Now, ammonium. So look at here, guys. This is another thing you have to be careful with it. 0.1 molar NH4 NO3. This will dissociate to 1 NH4 positive and 1 NO3 negative. So here it will be 0.1 molar. Be careful. If I have, for example, CaCl2, let's say, for example, like this, or CaNO3 by 2, or Ca, let's say, let me do CaF2. This one will dissociate to, and we have 0.1 molar also. Look how it will work. Ca 2 positive and 2F negative. So here will be 0.1. Here will be 2 times 0.1 molar. It will be 0.2 molar. So be careful. We need to know what we're gonna put here. So here, ammonium 0.1. 0.1. Here, 0, which is 3, 0, minus x plus x plus x, 0.1 minus x. Here, x and x. Now, also, look at here, guys. Another thing's important. Look what we have here. We have H3O positive, which is the H positive. So here, we need to use the Ka. If we have OH, if OH release, we will use the K sub B, not Ka. In case if you don't have the K sub A, it could be a K sub B, for example. Don't forget the relationship. K sub A times K sub B give you what? Give you K sub W. So be careful with the situation also. So here, from this situation, K sub A will equal x squared divided by 0.1 minus x. Now we need to see if we're gonna do approximation or not. So here, this one, the Ka times 100 will be less than the 0.1. So I think we are fine. So we will do the approximation. So here, that means it will be x squared divided by 0.1. Okay, so that's what we have, or what we did. And we did our approximation. So the Ka, it is 5.6 times 10 to negative 10 equal x squared divided by 0.1. Now x will equal the square of 5.6 times 10 to negative 10 times the 0.1. X will equal this amount, 7.5 times 10 to negative 6. And that will represent the H3O positive. And that will also represent the NH3. Using pH equal minus the guarantee 3O positive, pH will equal 5.12. So this is the pH for that salt solute. Percentage deprotonation, it is this amount divided by the initial, which is 0.1 times 100, we will get 0.0075%. So we are okay, less than 5%. Okay, now let's go and practice with the next assignment. Okay, estimate the pH of 0.2 molar Kf solution. Write the equation for each ion. Excuse me. So potassium, which is coming from strong base, so the potassium will be weak. Conjugate acid with the water, give you H3O positive, plus KOH. Now KOH, it is strong. Now that's impossible to happen, to go from weak to strong, so no, we will ignore it. Now another possibility, the F minus. F minus, it is kind of strong. Why? Because it's coming from weak acid, which is the HF. So here, strong conjugate base with the H2O, give you OH negative and HF, which is weak. So both weak, so it's going to be possible. The F negative is not very strong, guys. Okay, so that's why it's weak. So, but kind of it is stronger when we compare it, for example, with the K positive or another. Okay, so we will have the F negative plus H2O give us OH negative plus HF. Let's make the I stable from that. Okay. Here, nothing. Water. Now let's start with the fluorine. K sub F is associated to give you 1K and 1F. So if I have 0.02 molar, so this is 0.02, this is 0.02. So the fluoride will be 0.02 and 0, 0. Now, minus X plus X plus X, equilibrium, 0.02. Here X, here X. And the Ka will equal, here minus X, sorry, square divided by 0.02 minus X. And we will look for the approximation. If it's valid or not, we need to compare the initial concentration with the Ka. Here we don't have it. We can show you in the other slides. So this is the Ka sub B. Don't worry, guys. I have to give it to the K sub B. Okay. So K sub B, it is 1.4 times 10 to the negative 11, which is, of course, times 100 would be less than 0.02. So we will ignore the x in our calculation. K sub B will equal x squared divided by 0.02. And x will equal root square of this, and x will equal 5.3 times 10 to negative 7. So be careful, guys. Look at here. Here, oh, I have to use K sub B. In case if they give me Ka, we're going to use Ka times K sub B equal Kw. So don't forget, we can calculate it. Okay, so this x will represent the OH. Now let's look the logarithm, minus logarithm, the concentration of OH, and we will get the POH. POH equals 6.3. Then we know the pH plus POH equal 14. So we will use this relationship to calculate the pH. pH will equal 14 minus the POH, which is 6.3, and then we will get 7.7. That is the pH. Now, just to check if our approximation or not, or calculate the percentage of ionization or deprotonation. Forget this is sometimes we call it ionization, percentage ionization, or percentage deprotonation. The value here so it's going to be 7.56 times 10 to negative 7 divided by 0.02 times 100, we will get 0.0038%, which is less than 5%, so it will be valid. Okay. Now let's look for this example for the polyprotic acid. Polyprotic acid, it is the acid that can protonate more than one hydrogen. Be careful, it's supposed to be protonate more than one hydrogen. So for example, if you have H2CO3, this is diprotic, polyprotic, of course, but diprotic also because it can give two hydrogen plus 2H positive. But look to this one, acetic acid, CH3, COOH. It has four, but can only deprotonate one, which is only this one. So here, I'll give you just one H positive plus CH3, COO negative. So be careful, guys. Okay. Look at this example. Protonated glycine, which is NH3, CH2, COOH, is a diprotic amino acid with Ka1 equal 4.5 times 10 to negative 3, and Ka2 equal 1.7 times times 10 to negative 10. Calculate the concentration of all solute species in 0.5 molar NH3CH2 COH. Now, calculate all. So what we have here. So the first protonation will be according to this equation, and the second protonation will be according to the second reaction. Now let's use the ice table for the first deprotonation. So here, quick check that. Quick check Ka. So Ka times 100, it's less than 0.5. This is the Ka. Sorry, this is the Ka. So it's less than 0.5. So we shouldn't have to use the quadratic equation. It's close enough to check the 5% and the quick way. Okay, now we have the 0.5 molar here. Because H3O positive. And NH3, I'm just looking to the formula here, guys. Okay, I think there is a mistake here, guys. Okay, just 1 minute. Yeah. So here, okay, guys, here there is no Cl. Yeah, sorry. It is this one. Okay, and that one, of course, will dissociate to give the H3O positive. Yeah, there is no Cl here. Be careful, guys. Anyway, okay, so 0.5, 0, 0 minus x plus x plus x. Here, 0.5 5 minus x, and that will equal approximately 0.50. Here x, here x. Now we will use the Ka1 equal to x squared divided by the 0.5. We have the Ka1, we have it. So we can calculate the concentration of H3O positive and NH3CH2CO negative, because we need it for the second rotation. For here, we need it. Okay, so we will do the math and we will calculate the x value. Okay, let's go next slide here, and let's look at what we have. We have the Ka1, which is 4.5 times 10 to the negative 3, equal x squared divided by 0.05. To the math, x will equal 0.047. Now, the problem when you check the 5% or the deprotonation percentage, or the 5% rule, you will see like 0.47 divided by 0.5 times 100%, at times 100 will give you 9.4%, which is more than 5. So we'll have to use the quadratic equation. Always, guys, check. Not always when you multiply the constant K times 100 less than the initial will work most of the time, but you have then to check. Now we have to use the Ka equal 4.5 times 10 to negative 3 equal x squared divided by 0.5 minus x. So we will use the quadratic equation and have x equal 0.04, and that will give H3O positive and NH3 CH2CO negative. This volume will go to the next ice table. For the initial, for the original acid, NH3CH2COH will be at the equilibrium 0.5 minus 0.045 and equal 0.46 molar. We need the concentration of all solute species, guys, so they need it. So we have this one. This is the first one. Now get these, need to calculate it. So let's go to the other slide. Okay, now the second dissociation equilibrium reaction was this, dissociated with H3O positive plus the NH2 CH2CO negative. This was 0.045. We get it from the first dissociation. Here 0.045. Here 0 minus x plus x plus x. Here also minus x, and we will assume it is 0.045. Here 0.045. Here x. We know the x, it is the amount of dissociation, is the small. So Ka2, it is very small. It's 1.7, it's 10 to negative 7. So we will do our approximation. Hopefully it's working. Ka2, 1.7 times 10 to negative 10. 0.45 times x divided by 0.045, and the x will equal the amount of Ka2. By the way, guys, this X here for this one, this concentration of NH2, CH2, COO2 negative can equal the Ka2. You guys write it from the beginning or do this. It's better to do the ice table, but usually equal to Ka2. Now, all concentration of all species. So what do you have? The acid, we calculated, H3O positive is going to be from the first table, 0.045, or it will be 2.3 times 10 to negative 13. This species 0.045, the species which we took, it's equal to the Ka2, which is 1.7 times 10 to negative 10. Now the pH minus regarding the concentration of H3O positive and equals 1.35. Okay, so let's go and look for this example. Okay, what is the pH of 8.0 times 10 to negative 10 molar HCl solution? Now, look here. HCl here, it is a strong acid. But look at here, it is very diluted solution. So here, it doesn't make sense that the pH will equal approximately around 8 because it's acid. Now 8, it is a basic. So be careful. We have very diluted solution or acid, we will use this equation. The H3O positive to power 2 minus HCl initial times the H3O positive minus Kw equals 0. And that's equal to x squared, for example, here, minus 8.0 times 10 to negative 8, which is the initial concentration of HCl, times x. This is the x. Minus the Kw, which is 1 times 10 to negative 14 equals 0. Solve with the quadratic equation. We have the x will equal 1.5 times 10 to negative 7. And that will represent the concentration of H3O positive, which we needed to calculate the pH equal minus regarding the concentration of H3O positive, and that will give us 6.8, 6.82. So look at here, this is the pH. Now pH around 8. This is still acidic because it's less than 7. So be careful, guys, when we have diluted solution. Diluted solution, you will use this formula. Okay. Now, for a basic solution, diluted basic solution, so look at this example what we have. What is the pH of 2.7 times 10 to negative 7 molar NaOH? NaOH is a strong base. And don't tell me here it will be around pH equal 7, because this is strong base, okay? 7 or less than 7 will be neutral, so it doesn't make sense. So here, because it's very, very diluted solution, how you know it's a diluted solution, guys? When you have the concentration for acid or base around or less than 10, -6, less than -6. So here, 10 -7, in the previous example was 10 to -8. So when you have this amount, so you will use these formula. So for basic, we will use the H3O positive to pore 2. Here NaOH initial times the H3O positive concentration minus the Kw equals 0. So here we'll represent the X squared, here the amount of NaOH, and here the X, here the Kw. Solve the problem using the quadratic equation. We will get X equal 4.1 times 10 to -8. Now, of course, this will represent the H3O positive, and that one, we will use it to find the pH. pH will equal minus together the concentration of H3O positive minus together the 4.1 times 10 to -8, and it will give us 7.39. So look at here, it is 7.39. It is more than 7. So for that one, I think it is supposed to be more than less than 7. So it's around 6, maybe. You can check it. So right now, more than 7, it is a basic, because the 7 is in the neutral. So right now, it does make sense. Here, acidic, less than 7, and here, basic. Sorry, no, here. Like this, here, basic. As I said, guys, that's how you will deal with these type of very diluted solution. And you will go and see how it will be diluted when you have the concentration around 10 to -6, 10 to -6 or less.